Okay, so everyone, welcome. Okay, this is for my part, right? As I mentioned to you, everyone, I said this is for my part. This is for my lecture class. This is my last lecture class, right? Then, okay, a few important things to remember. All right, but nearer the time, we will also remind you again. As I mentioned to you all last week. Before that, before I forget, otherwise I will forget. Okay, as I first of all promised you, I said I have asked my GAs to be here so that at least for a short while you can have this introduction to them. So my GAs are here. You see Miss Zhang Xiaoxue, Dr. Wang Wenxin, Mr. Cheng Zilong. So they will be the persons who will lead the. They will be the persons leading the ELAB sessions, right? Leading the ELAB sessions. So we are at this stage today, right? Today's lecture class. Then ELAB sessions are next week. All right. So they will be the persons who will guide and lead you on the ELAB session. So here, I've asked them to be here just for a short while. All right. And so that you have this introduction very quickly to them. Then afterwards, I will also describe, okay, in at least a bit of detail, first of all, right? In a bit of detail, first of all, the actual CA1 and CA3, right? Then when I'm finished with that, I will just let Xiaoxue, Zilong, and also Wenxing just exit because they have other things to do also. All right, so they are here. Thanks to them, and great to have this introduction to them. Okay, now go back to what I was talking about before. So remember last week, right? Remember last week I had mentioned that, okay, remember for the exam ahead, all right, to note that it will be an in-person exam at an appropriate venue in NUS, which will be informed to you all. Okay, then it will be in person in the classroom, all right, and it will be closed book, and in accordance with all the usual pathways in which we have done it, all right. Although closed book, you are allowed to bring in your own A4 sheet, double-sided, of whatever notes you want to put in. And remember last week I reminded you it should be one A4 double-sided. Don't be too clever, otherwise the administrators can reject it, right? So one A4 sheet double-sided, but also very important would be that in order not to waste the one A4 sheet double-sided space that you have, go and download when you have the time the other year's exam papers, and you will see that already in the exam papers right at the end, we already have a lot of additional detailed information. So no point for you to duplicate that additional detailed information and waste the space that you have in the one A4 double-sided. Okay, so that part of it. Then of course, okay, then today I will actually go and point you to a lot of further possible material. All right, so I've uploaded that, but you also saw that, you know, I'm very, very clear. Okay, I'm very, very clear. These things that I upload, okay, I straight away guarantee you that they are non-exam material. Okay, I will go through this today because they point us on the way forward, because we have basically built all the important foundations, right? All the important foundations. So I'll point you to all the possibilities and developments forward. But as I said, I guarantee you can see this in black and white. These are non-exam material, non-exam material, non-exam material. Okay. So as I said, I'll go through this. I'll look at those things. I'll kind of talk about those matters and the review and revision. Okay, but again, just to remind you all again that, look, we are at this stage now, today's class, right? We are at this stage, today's class. Lab sessions are next week, all right? And they will be taken by my GAs. So my GAs have kindly, join into this Zoom here so you can have this introductory session with them, right? So these are the ELAB sessions. They will guide you carefully, right? They will go through, then they will even lead you through various steps on how to set things up, and also guide you on relevant matters on that. Okay, so with that, let me then straight away go into, okay, let me remove the sound. Okay, no more sound. Okay, with that, then let me actually go into describing, as I mentioned, at least some kind of detail, all right, the lab sessions, the CAs, right, the CAs requirement, I mentioned that, describe them, my GAs are here. Then after that, I will let my GAs leave because they have things to do as well. Okay, so now going on to this, okay, you will see these were files you already have. This is the CA1. Okay, I pull up the 6104 here. All right, 5104 is similar, except it is essentially just missing the later parts, right? Then I will also pull up the CA3 file, okay, CA3 file, right, with its accompanying materials down there, the second file, right? Okay, and I'll mention it. Okay, let me first talk about CA1. So CA1, well, although it's called CA1, actually, as you already saw, this is adaptive control with only input-output measurable. So in some sense, the theory behind this is a more difficult theory. All right, but never mind, let's call it CA1. All right, and then CA3, actually, the theory actually is simpler, but I do want you to, okay, even though we're not using the lab, the hardware, I do want you to make it as close to actual hardware situation as possible, so you can actually see some of the real things that actually would come up lah. So that's why I put it that way. Okay, and then of course in the lab session, all right, essentially I told Xiaoxue, Zilong, Wenxin, they all first of all to describe the CA3 because it's actually the easier one. All right, it's actually the easier one. So they will describe it and you can get it set up and get moving. All right, get moving. Then in the second session, they will point you to some further CA3 areas. All right, but some of you by that time, once you get started on your CA3, you will also be very confident and quite ready already, right, to do your CA1 material. So in the second session, if you all want to also request for some discussion by my GA and some guidance by my GA on CA1, that's also possible. All right, because we have done this in this way in earlier years. Okay, now let me now, for now, then just go to CA1. So CA1, I asked you to essentially look at a system like this, input, output, measurable, right? So you clearly can see, okay, so in the simulation, this is what you will do. This is what you will use. All right, so you can clearly see for the system, all right, in terms of what we had described previously before, this is a relative degree 1 system, which means that strict possibleness actually applies, right? And you can use those methods down there. So here I said, okay, go ahead, write down all those details, all right? Okay, of course, in simulation, you know all of these things, all right? But in real life, okay, even if you were working with this, pretty much all you see is the input output. So basically, in real life, probably you can have information like this to say, look, you know that the system, the plant is actually stable, except that, the damping is very, very light and natural frequency is approximately 2 radians per second. So, I mean, it's not exact, but, in real life, this is what you might know. Then, as I told you all earlier in class, use any programming language. So remember, I told you in earlier years, we had one GA, Dr. Lin Feng now, and he used the C programming language. That's fine too. It's completely up to you. Okay, but of course, essentially life is much easier if you use MATLAB and even the graphical version of MATLAB. So I said, okay, go ahead and begin to explore these things, all right? But as I also noted, when we developed the theory, I said, look, this is basically a simulation project. And, you can reverse calculate many of the things so that you can explore all these things in your simulation. So that's why I suggested here. And I said, go and look at the observer polynomial, right? The 1 over t polynomial filter, right? Investigate different choices. Then, put in some reference signal, which is like this, see what happens. And it's actually quite exciting because you really see what we had developed in theory actually happening. Then, of course, for 6104, I go on to say, look, can you explore more? All right, explore more. And then as you explore more, it's not just doing more, as I said in class. All right, not just a question of doing more. As you begin to do all of these things, okay, go and look into there and tell me what additional things are happening and tell me why. All right, so this is the expectation of 6104. All right, and then of course also to say, look, okay, supposing, and it happens, right? It happens, suddenly after you've operated for a while, suddenly the system changed. All right, and then go and investigate carefully, okay, for 6104 and see what happens and also tell me why. All right, and of course, everything, write me a good report. Okay, write me a very, very good report. All right. Okay, maybe at this point, I will even pull up what I had described in the very first class. All right. Class number 1, I said, we are very, very kind. All right. Because what I had done was I had, all right, in addition to all those things that we had, I had asked one of my earlier GAs, Dr. Sun Lu, all right. Of course, before that, he was a 6104 student, so he had done a lot of the work, all right. So probably some of these are from his own report. So I said, Sun Lu, put together for me a very detailed report that will guide the students. So you see this down here, this is very, very detailed, all right, which I said down here can help you to, very, very detailed, can help you to write your CA1 report even. Okay, let me now very quickly show this down here. Or you can download this, So you see here, Sun Lu has put for your CA1, all right, together a very, very detailed report, which is 43 pages. So certainly, with enough information for you to write a lot of things. So this CA1, all right, so essentially, Sun Lu put together the developments very clearly, very carefully. All right, okay, the controller canonical form realization of the 1 over t filter, right? Then basically calculating in detail, all right? Sun Lu calculates in detail. Okay, this is basically the ideas from proposition 1 and 2, remember? Right, ideas from proposition 1 and 2. So Sun Lu shows that for you. Okay, then develops that. Okay, and Sun Lu has his own Simulink. There are many ways to do it, but so this is just, take this to be just a Simulink implementation realization. My GA Xiaoxue Zilong Wenxing will show you more, all right, some additional things. This is, but this will get you going and already got quite a lot of things to do, right? So, well, Sun Lu shows you the non-minimal state realization, and he shows you some of the results that he himself got, right? And then he, you can see down here, he talks about some of the methods and some of the thoughts down there, right? So as I said, here, basically you need to do the work yourself, all right? Then it becomes very, very clear. But after you do the work, okay, it's useful to pull up this very detailed write-up by Sun Lu. All right, very, very detailed write-up by Sun Lu. And then in your report writing, it will help you to write a very good report. All right. So as I emphasized many times before, I said, you know, both Buffo and myself, we are very, very willing to, you know, give you credit and even find out and try to look in all your reports to give you that credit. But, you know, in order to be able to do that, you jolly well put in your own work and write us that good report. Because as I said, you know, I mean, here even for Sun Lu, even in this set of briefing notes, he already put in 40 over pages. If let's say even out of your own work, you just give me 3 pages, how many marks can I give you even if I want to be kind? So you can imagine. Okay, so okay, all these things are here to help you. All right, so that's CA1. Okay, for CA3, okay, in the early years, all right, in the early years, and that was the time when Wen-Sing was actually a student in the module. Wen-Sing also took adaptive control systems. So Hao Ren, Jia Hui, Dr. Zhu Haiye from SimTech, who is guiding you now, was also my student in adaptive control class. So during that time, because there was no such thing as COVID, we actually forced them to go to the lab and they actually work in the lab. Okay, it's quite interesting because you know actually really see the thing working in real hardware. Okay, but because this time, okay, suddenly COVID started, so I had to kind of change this thing, right? I had to change this thing. So, okay, but I wanted to capture the things as much as possible. So that's why I said, okay, even though the theory is simpler, I want you to put up a situation such that it is as close as possible to the real hardware. So for example, certain things that will already be in the hardware, okay? So my motor down there, okay, my motor down there, basically the drive input is plus minus 5 volts. All right, if you now go and try to do unrealistic, fantastic adaptive control. So you see all these things are very real, okay? Very real. It tells you that, look, you know, my motor in the open loop, all right, open loop for the velocity part is basically 0.25 seconds. So if let's say you say, okay, the theory says everything is possible, you say you want to drive this whole thing to 1 nanosecond. On paper, it will be possible, but you know what will happen is that, you know, you can explore. All right, what will happen is that some of your drive inputs are, instead of within plus minus 5 volts, you may need 1 million volts. And in your simulation, it will come out, but when you put on the motor, the whole thing is just going to, you know, I don't know how. So that's why I want you to build in all these things, all right? So that's why I said you go and compare to the motor. Right, then also, I also want to make it very, very realistic because no matter what kind of fancy control you are using, I don't even particularly bother because in my early days, I also, because some of the motor you can put it with such that it's not evenly loaded, all right? Because basically in the robotic arm, basically it will not be evenly loaded and it will depend on the position of the loading. All right, so in my early days, you know, I had even put together, all right, radio basis functions, neural networks, and done an equivalent of a non-linear adaptive controller for that. But okay, whether you have non-linear adaptive controller, fantastic, whatever controller, okay, even before you try to do that, you have to do the one basic thing, all right? You have to go back to the motor and make sure you know what this motor is doing for you. And you have to, okay, so that time when Wen-Sing and Dr. Zhu Haiye were students in my class, okay, the first session, nearly 2 hours, was just carefully calibrating the equipment. All right, and you have to do that. You have to carefully calibrate the equipment because, you know, that's where I again put in the second file. All right, so to remind you, all right, that look, you know, I want this to be as close as possible to the real thing. All right, and even though, okay, when you simulate, you will simulate this. But even in this simulation, you can well imagine in the lab, basically this is the motto, even though you model it like this is the motto, okay? And in the motto, the only thing you can say is that you can put in the voltage input. That's the only thing you can say. And your voltage will have to be within plus minus 5 volts. That's the first thing you have to say. That's all you have. And then what comes out down here as a so-called potentiometer measurement is also voltage only. And what comes out of here as a tacho generator, which is the angular velocity measurement, is just a voltage. Okay, so this is all you have when you go to the lab. You apply a voltage, you get 2 voltages coming out. So that's why I say, even though the theory for CA3 is simpler, I said, look, go and at least have some sense of the real thing. Look at all, and of course, now, because we don't have the motto, I make life a little bit simpler for all of you lah. I said, okay, you can go to the files. So instead of like Dr. Wang Womin Singh, Dr. Chu Haiye time when they were students, they had to spend 1 or 2 hours doing the calibration. All right. So instead of that, I said, look. Okay, I actually have calibration data. And when you're calibrating, you have to set up equivalent of a real-time Simulink setup like this, which is LabVIEW. LabVIEW is real-time Simulink. You have to set it up, all right, so that you can do the calibrations. All right, and you can see this was part of the calibration, and these were the calibration results that come out for the angular position potentiometer. All right, and then you will see these are the results that come out of the angular velocity, the tacho generator. All right, so I said, look, you have now in this second file all the calibration data. And, in your CA3, I don't want you to simply just, go and simulate, okay? I don't want you to just simply go and simply simulate the system like that, all right? Like that, okay? Because I want you to, of course, you're simulating this, but I want you to work with the situation that all you have is a volt coming in, voltage coming in, voltage coming out, and you work with the calibration data. All right, make sure that all of that is in the work that you do. So as I said, yeah, you go take my calibration data in the file 02, all right, and then bring it back into whatever simulation you're doing. So actually, essentially, even in a simulation, you're just working with voltages. All right, then go ahead, do the adaptive control. All right, this is adaptive control with full state variable measurable. All right, go and set up this will be Simulink now, of course, because it's simulation. All right, but of course, if you want, you can also program it in C, that's fine. All right, so any simulation language, all right, any simulation language. So go and do that. And for 5104, you explore this, look in detail, and then let me know. All right, describe that in detail to me in your project report. Okay, 6104, again, I'm not just asking you to do more, I'm pushing you further. I'm saying for the same setup down there, okay, then I keep it simpler. All right, for the same setup down there, I keep it simpler. I said, just look at control of the angular velocity. All right, so it's simpler. All right, it's not the whole thing, it's just the angular velocity no longer involving the position. All right, so I said, you go and do that, set it up. Then after that, I said, look, and that can be set up very simply, okay, very, very simply. Then I said, okay, more than that, okay, I now want you in this angular velocity adaptive control. I said, no, I want to do more. All right, I want you to now add in integral control action. So the whole idea of your control systems, because all of you told me you know control systems very well, right? So certainly this part what will come in is that the whole idea of the augmented system has to come up. Okay, with the augmented state variable has to come up, and then you have to go and look at it and ensure me that even with setting up this new augmented error signal that you still can somehow set it up properly for adaptive control. And you can, I guarantee you can. But you just have to show me, okay, in 6104, how it can be done, showing me, okay, all the proper rigorous design equations. Okay, so that's why CA3 has 2 files, all right. this first file here describing what I want you to do, but is to be closely tied in, as I said, with the actual situation of the real motor, all right, with all the calibration data. So I want you to work as though this was actually really, okay, really that situation of the real motor. Okay. Then similarly, as I also told everyone in the first class, all right, I said, okay, I'm not leaving you alone. All right, just as for CA1, okay, just as for CA1, all right, I have detailed guiding notes by Dr. Sun Lu to assist you. All right, similarly for CA3, I also asked Sun Lu to go on further, all right, and also write up the detailed guiding notes. And you see here, Sun Lu has written nearly 60 pages for CA3. All right, so of course, during his time, he was actually doing it also really on a motor, but what you are doing is very similar, just that it's converted to simulation. So carefully look at it. Whatever Sun Lu has in here, all right, will be suitable as parts of your report as well. All right, Sun Lu even took picture of the Apuno. So you can see, okay, it's all there. All right, so Sun Lu has carefully put all of that together and indicated Babala's lemma as well. And then put all that together, mentioning the programming, right? And in there, you can actually see, of course, he goes on to talk about a bit more. All right. Okay, so even for CA3, there is a lot of guiding material for you to write a very, very good report. Okay, let me now pause the recording. All right, so as you can see, all right, essentially, we are ready, right? We are ready for CA3 session, ELAB session, first session, then second session. Then second session, as I mentioned, right? By that time, you'll be very confident already, and probably you may have started some CA1 methods, right? So probably I will also remind my GAs that in any case, which they have done in past semesters, to start some guidance straight away on the CA1 for the second session. So you can see we are all ready. Okay, so as I also said, I said both for CA1 and CA3, right? We have supporting materials for you all, right? We have supporting materials for you all. Make sure you use it, all right? So we are all ready for that. Okay. Then all the other matters nearer the time, we will also remind you all. Then with that, let me now go on to these materials in my class today. All right, to my class today that I basically to bring to a very nice completion my part of the module, Okay, so okay, as usual, again, all right, go all the way back even to lecture 3, and that was about adaptive control of input with input-output measurable. So remember, that was how we set up the system, and this is your CA1, right? This is your CA1. So we set up the system, right? Then leading to what the perfect control law should look like. Basically setting this whole thing, right? Taking this part, setting it equals to this, all right? Which boils down to this control law. So this part of it is the perfect one. And these perfect numbers you can reverse calculate in your simulation, right? So we had that. So then I said, okay, in order to see this very clearly, simply look at the second order case. And indeed, this second order case, although it shows the details clearly, but yet, it entirely scales up, right? Entirely scales up. There's nothing lost in that. Okay, so we looked at that, which is also, okay, the other advantage of this second order case is this is also exactly what you're doing in your CA1 now, leading now to this diagram, right? Which I said, I reminded you that in some ways this diagram is very important because many details actually are contained in there, right? So you can set all of these things up, and then put it in the usual structure, all the signals that we have, and the gains, all right? Because when it comes to the perfect gains, it comes out like this. So we cannot calculate the perfect gain, so we put in time varying numbers. But these signals are things we generate. So we put in these numbers and we have to say how, right? We are adapting the control gain. So with that, we noted the two intermediate results, all right? First of all, proposition 1, all right? Then a proposition 2, which were all very important. All right, then with that, now, okay, again to emphasize that up to this stage, all right, it holds for general n order system. No requirement for relative degree equals to 1. Okay, except that when you now go past this and you now want to see a first stage, very, very simple adaptive control law, okay, then we say, okay, if the case is such as relative degree equals to 1, which is the case for your CA1, both for 5104 and 6104, all right? That if you do it like this, all right, then then the adaptation is very straightforward, all right? These are all the signals you're generating. This is the output error, all right? Reference model you set up, so you have reference model output. System output you measure. So you have E1, all right? So basically all that happens is that all these are all signals you have. This is the output error. You put in symmetric positive definite matrix. You simple test will give you the sign of KP, all right? Then you put that together and that's the adaptation and you're guaranteed this, right? So we said that, okay? We said that, which basically says, okay, and this is basically your CA1 too. Your CA1, this is what you're doing in your CA1, okay? Then remember, we pushed on further, right? We pushed on further, and the previous class, we said, okay, now when specifically is relative degree 1 and we can do what we're doing in your CA1, okay, we note the non-minimal realization, all right? And then you kind of arrange these things together. And suddenly you note that, hey, with the perfect control gains, it becomes your reference model. All right, so your reference model is like that in relative degree 1. Okay, and yet these are the equivalent things. All right, which means that, because by proposition 1 and 2, state feedback doesn't change a thing, doesn't change the order of the system. Order of the system still remains 2n. All right, so, therefore, your reference model itself also admits a 2n order non-minimal realization. So conceptually, this thing exists, except the big difference here is that, you cannot, even though it exists, you cannot actually use this to put your controller, all right? So this is different from the earlier case. Okay, you cannot use this to put together your controller. All you know is that this conceptually exists. Okay, so now, but nevertheless, you can go ahead to use this in your development. So you can put together the error models, right? Then noting strict positive realness, this will be adaptive law. You go ahead, put those things together, carefully check all of that, and you begin to see, indeed, all those properties are there, all right, including basically as you do, if you integrate the square, basically integrating the square, all right, of the errors down here. Again, you get the so-called Babalat's lemma, and you can get tracking error equals to 0. All right. So, okay, maybe I will emphasize again that you see in all of these things, my result has always been that even though this is a very difficult nonlinear system in terms of analysis, yet I can guarantee you that, look, I'm always able to work with the system because, the system does not kapung, escape away to infinity. At all times, my signal exists, and in fact, they are bounded even. So that's one thing I always had. And then I always could guarantee tracking error equals to 0. But you will also see that that's all I can guarantee. All right, even though we had all of these, you will see that, all the way, even you go back to lecture 1, even for such a simple case. All right, all I could say is that signals are bounded and tracking error goes to 0, which is what we want in control. All right, but insofar as adaptation of the so-called control gains is concerned, we were totally silent on convergence of the control gains. All right, because you couldn't say anything. All right, so that was that. Then remember, after that, last week I said, okay, let's back off a bit and begin to see what we have done. I said, even though we have done, specifically, we have handled adaptive control. But actually, in reality, we were handling a lot of signals and systems, even though we put them in the situation of adaptive control. Right, so you can see down here that now, all right, with what we have, all right, basically the structures that came up, all right, this is a structure that came up for adaptive control with full state variable measurable. All right, and you will see that once you come up with this equation, straight away you know that you can pair this as the adaptation equation. All right, because this comes as a adaptation pair. All right, you can go, of course, you can go ahead, do all the analysis. Then you also saw, and this came out of our adaptive control with only input-output measurable. All right, that essentially now you were saying that you were working with a linear transfer operator, linear time invariant transfer operator, which had the property of strict positive realness. All right, if it had the strict properties of strict positive realness, you can double check. Your equation was basically like this, okay? And then what was happening was that if you now get this, then the way to pair it was, all right, okay, let me. The way to pair it was if you had a strict positive real transfer operator, okay. Then what was happening was that if you had this kind of situation, this is how you would pair. And this was your CA1. All right, adaptive control with full state variable measurable. Okay, then I said actually, we had looked carefully in detail on signals and systems in our lecture 1 on the first order case. We did it very, very carefully so that we could see all the signals and systems. All right, but in reality, if you go back to your lecture 1 and carefully rewrite it, you will see that actually this is exactly the situation of strict positive realness. And it was exactly like this. It was exactly like this. And if let's say in lecture 1, I had told you strict positive realness, we would have solved the whole thing in half an hour. All right, but of course, if I had said lecture 1 and I said strict positive realness, I think all of you would disappear from my class. So I think whatever it is, there was still interesting value. And in any case, it's still very interesting to actually see the signals and systems, right? So it was like that. Then remember, I backed off and I said, look, apart from all those error systems above, you can actually even look at a simpler error system, all right? Just some tracking error, and then some set of parameter errors that you're trying to adapt, and some set of signals that you have, but coming through with some control direction, so to say. Okay, and this can be generalized, all right? This can be generalized to multi-variable system, in which in the case it becomes a control direction matrix, all right? And in later years, we've done some work on that. As I laugh with my student, Howren and Jiahui, I said, I started work with my good friend, Prof. Kasutsu. So he learned adaptive control from me and we worked together. And then, with some of our students, we did even more. And actually, some of my students are even better at adaptive control than me now. So we have even specialized this to the multivariable case where it's a control direction matrix. And they've taken my own very early results of my own PhD even, where, I basically invented the discrete Nussbaum game, but for scalar systems. So one of my students, together with Prof. Samger, has generalize this to the discrete Nussbaum gain matrix to handle the case of control direction where you don't need to use information of control direction. All right, so all these things can be specialized. So here, okay, this is even a simpler one. All right, and even in this simpler one, you see the idea of control direction actually comes in importantly. All right, and as I said, there's interesting research to be done, and we've done quite a bit of it. All right, but never mind. For simple cases, let's just say we have that sign, and you'll see that it comes out like this. But why I like this very, very simple error model, all right, as I mentioned to you all last week, is I like this for a few reasons. First of all, even though it's so simple, all right, actually once you handle it properly, all right, one thing would be that, okay, is stability analysis is quite straightforward. All right, but more than that, even though this is such a simple error model, the one thing that I really like about it is that once you really understand your signals and systems properly, right? So I was very glad when a lot of you, again, as I say, applied to join my adaptive control module. You say, Prof, I know signals and systems, so I was very glad. So as I said, you know, this simpler error system, it turns out that, you know, once you understand your signals and systems very, very well, you can actually use this actually even for the much more difficult case now of relative degree greater than 1. But of course, now you have to do it stage by stage, looking at the signals and systems very, very carefully. So that's one of the first reasons why I like, all right, why I like this final, simpler error model. But the other reason why I like it, as I told you right at the end of last week's class, was because it's so simple. Okay, so straight away, similarly, you know, you can go and do the stability analysis and you can still get, you know, the Babalat's lemma kind of thing, because you're still integrating E1 squared, all right? And you can still get all these properties that E1 squared, E1 is tending to 0. Okay, so you still get tracking error going to 0. You still get the kind of results that we have. But, all right, and even in this simple case, all you get is the tracking error going to 0. That's all you get. All right, so you go back down there, okay, there's still the parameter error. And the stability analysis coming out of it guarantees you tracking error will go to 0 when you pair it with the adaptation like that. But still, you cannot say anything about convergence of even the parameter error. And what is nice about this simpler one is, okay, even though you cannot say anything, as I told you last week, I said at least you can begin to see that, you know, out of the stability analysis, I guaranteed you, all right, because I integrated the square of the tracking error, I look at boundedness of the signals, all right, and because it is E1 is L2 signal, all right, square integrable, and then E1 dot is L infinity signal bounded. So indeed, as we said before, okay, a signal which is square integrable, its derivative bounded guarantees you that it will converge to 0. So E1 is like that. All right. But here E1 goes to 0. And you see, this is so direct. Kp is just a number. E1 is going to 0. Oh, omega, the signals in omega are all your signals. They are not 0 because you are generating them. All right. Somehow, some way, you're generating them. Okay. And yet you cannot say anything about the parameter phi going to 0. And you can see why. Because, you know, E1 is going to 0 is guaranteed out of your analysis. All your omega signals are measurable signals generated by you. When E1 goes to 0, the only thing you can say is that phi transpose omega goes to 0. That's all. That's the only thing you can say. You can only say phi transpose omega is going to 0. There's nothing you can say about phi going to 0, even here, even in this simple one. And remember, I then told you, I said, look, you know, you can see this situation very, very clearly. Okay, let's say you have 3 signals. Right, 3 signals in here, okay, as you saw, 2n plus 1 signals, right? So you know, your Y signal, your U signal, and your R signal, so 2n plus 1 signal, all right? So your 2n plus 1 signal down here, 3 signals, all right? So 3 signals would live in a 3-dimension space, and it generalizes to n dimension, except we can't easily visualize it. So your three signals live in the three-dimension space, okay? And you are guaranteed that this tracking error is going to zero out of your analysis. Then with your three signals, living in this three-dimension space, supposing it is a strange kind of situation where you have three signals, but your three signals somehow, all right, because your three signals are actually coming out of a dynamical system, all right, and they're somehow related if you don't meet certain conditions. So if you don't meet certain conditions, even though you have three signals, your three signals can all be living in a two-dimension plane. And then what will happen is that, because as a result of this adaptation, you are guaranteed that the tracking error is going to zero. So your three signals are still running all over the place, but staying in a two-dimension plane. Then all that will happen is that the parameter error will also adapt. But it will adapt such that, it will begin to, has to obey the fact that E1 tends to zero. But it will now adapt and basically rotate until it becomes, first of all, a normal vector to the plane in which your signals live. And as long as it's on that normal vector to the plane on which your vector lives, there's nothing you can say about this parameter error going to zero because it's happily living in that normal. And it's allowed to live in a normal because E1 is still tending to zero. All right. And that's where this very, very rigorous concept of persistency of excitation comes in. All right. So as I mentioned last week, I said, this concept of persistency of excitation, unfortunately, because of this choice of English words. So some people, you'll see in some journal papers, some people say, oh, my signals are persistently exciting because they're jumping all over the place. It's rubbish. It's rubbish. Okay. Persistency of excitation is not that your signals are non-zero and jumping. No. It says that, look, if you have n signals living in an n-dimension space, if you claim that living in this n-dimension space, your signals are persistently exciting, then you have to exactly obey this. All right, in whatever dimension that you are operating in, you must obey this, because what I'll do is I'll find any vector. All right, and for simplicity, I say a unit vector, but it doesn't really matter. All right, I take any vector, all right, any unit vector living in your n1 space, all right, and I'm allowed to take any n1 vector. Okay, if it's such a situation where I can find an n1 vector in your n1 space such that when I put a vector, the projection component, cannot be guaranteed to satisfy this kind of projection component, then you don't have persistency of excitation. All right, persistency of excitation basically says that in this n space, your signals must all be moving around so that any direction that I pick, there's always a minimum period of time. There's always a minimum period of time for which there's a projection in any direction that I pick. And that then is rigorously the concept of persistency of excitation. Okay, with that, that's called a... Okay, so let's push on. All right. So we talked about these things, right? And I've talked about, okay, if we, particularly if we now, basically it's almost like taking a few steps back to see what you're doing, all right? So even though we are focused on adaptive control, but basically at the end of it, the type of signals that came up were basically pairs possible for stable adaptation like this one, right? Then of course, remember, so we had seen that, right? Then of course, we had also seen how with strict positive realness, right? The kinds of things we could do, but that was restricted to relative degree 1, right? That was restricted to relative degree 1. Then remember I mentioned, I said, look, relative degree greater than 1. It's also possible to do. And in the early years, I used to, when I was young, I was very fierce lah. When I was young, very fierce lah. So 6104 people that time had to do that, but then I decided no point. I just want you to observe and understand the key things in there. There's no point to force you all to do a lot of messy adaptation, signal processing. But as you can see, once you carefully rearrange and process the signals, all right, it's possible now. Okay, and as I said, this is the simplest error model now. If you look at this exactly, some of these are exactly after you rearrange it, all right, it turns out to be like this, which is nothing more than the so-called simplest error model, right? And of course, then you pair in that way and you solve the first stage. But that's only the first stage, all right? Because when it comes to relative degree greater than 1, all right, it has to be broken into many stages, and you have to carefully do your signals and system. Okay, at this stage, let me remember to mention again my promise. Okay, relative degree greater than 1, both for 5104 and 6104. Both for 5104 and 6104 will not be in the exam. Okay, in fact, all these things down here will not be in the exam. Okay, so as I said, you can break it up stage by stage, do the signals and systems, and you can see that. And then once you've done this first stage of signals and systems, you have to carefully see the properties resulting from it, all right? And the function classes of signals, L2 signals, right? Then once you have that, you actually have to go on, all right, to kind of look at ordering relations of signals. So this is signals and systems again, but very, very careful and detailed signals and systems. And once you have that, you carefully now begin to track the ordering of the systems, and even for relative degree greater. Okay, this was last time. Okay, so now here, even all this part, all not necessary for exam. So 6104 last time was like that, but no more. All right, you get that. Then okay, supposing you said, look, I don't want to have such a hard life, sticking with always having to rigorously prove everything, right? And then you say, look, can I do it simpler or not? So it's also possible, right? So which is some of the other things that I've showed in here. Okay, so as I said, all these, I promise you when I uploaded it, I say all these are not for exam. So similarly, you can have a system. So you no need to go ahead and try to use Kamal Yakubovich lemma, use detailed signals and system. You can say, look, supposing the system is like that. So I don't even rearrange it in monic form anymore. I just leave the parameters as they are, because then you can rewrite the system, right? For example, you can rewrite the system, then you can basically choose a higher order filter than whatever is here. Actually, you don't need order n+1. If you rearrange it carefully, actually, if you have order n is good enough, but never mind, I do an overkill, I do an order n+1. And the moment I do an order n+1 and stable, okay, I can filter both sides. And as before, once I filter both sides, I can generate all the signals that I want. And the moment I generate the signals that I want, I can rearrange the parameters like that. All right, and all these are signals that I have, because these are generated from what I have above, and then these are the parameters of the system. Okay, then the moment I have that, I can say, look, this is already in a very convenient form, all right, and using some of the, so as I said down here, actually you can use n order filter. Okay, I'll let you go and think about it. But anyway, the important thing is that you arrange it in a so-called linear and a parameter structure. You put it like that, and once you have it like that, actually you can set up a very nice stable estimator also. All right, you can set up a stable estimator, and then once you have a stable estimator, then okay, you can go ahead. You have estimates of A1, A2, B0, B1, and once you have estimates, you can do anything you want from your 5101, from my 4302, anything. All right, so because you have estimates, so as I said, these things are also possible to do, which is basically what I had said in this next part, that you say you don't want to suffer and always show all those things. Okay, you can generate estimates. All right, and then my estimator, one way I can construct it is that it is a very well-behaved estimator. Then you can combine. Once you have the estimates, you can combine the control. Okay, that's what I first of all wanted to mention. Okay, and that would be many other ways to do it. Okay, so those things will be possible. Then going on further. All right, what about discrete time systems? All right, in the early days, I used to cram all of this down, but now I just say it is all possible to do. All right, and just tell you it's possible to do and show you that it's possible to do. And also my promise, not for exams, not for exams. Okay, so typical discrete time system looks like this, right? Okay, now when you work with the backward shift operator, certain things are not so obvious. All right, but never mind, all right. In fact, there's an equivalent so-called visual identity, except that you don't see that it is the same as what we had before because you're working with a backward shift operator. All right, and until you say, look, just go ahead and convert everything properly, so that it looks the same as what we have. And to convert it properly, you basically take the whole thing and multiply through. And when you multiply through, you will see that you are left with equations in the forward shift operator. All right, and the moment when you have equations in the forward shift operator, you take the equations in the forward shift operator and rearrange them. All right, you go and compare and you will see, you take that equation, okay? So this equation is left-hand side, a polynomial of degree n plus d minus 1. This is of degree n, which is the quotient. You take a polynomial on the left-hand side of degree n plus d minus 1, divide by a quotient of degree n. Of course, you know, this divisor of degree n, of course, the quotient will be of degree d minus 1. And the remainder, of course, will be of degree n minus 1 and be like this. And you can go back and see now that, you know, once you've done that, this is basically that proves that so-called Bijou or Diophantine identity for you, even in discrete time. So once you have that, again, actually, you can proceed as before, equivalently, and you will get that so-called equivalent, you follow through, all right, so-called equivalent perfect control law. Okay, and let me push on further. All right, which is here. All right, so as I said, you know, once you have this here, all right, which is the next file, again, my promise, not for exam. All right, you work with this, all right, but you carefully now go ahead, first of all, to be clear that you can use this so-called equivalent prediction identity and again work with it, rearrange. And you will see, if you work carefully, you will see the parallels, all right, to what we have done carefully for our continuous time system. All right, continuous time system, adaptive control with only input-output measurable. All right, so again, you will see a control law and adaptive law. All right, and it will look like this. It will look like this, all right, and the structures are similar. Okay, structures are similar. Okay, adaptation, partly similar is more similar to the relative degree greater than 1 case, but partly similar. All right, and it will look like this. Okay, so instead of theta dot, it becomes how you increment it. So this is how you increment it. And because it's discrete time, you will need some kind of a normalization. All right, and you will see it coming out in a moment. You will need that normalization. All right, you will see that this is needed. All right, in some ways, for those of you who are familiar with stochastic updates for maximum likelihood estimators and things and so on, you might see some familiarity. So again, this is an n+1 vector of signals that you have. This is always the vector of signals that you have, all right, which is generated by you, okay? This is the 2n+1 vectors. Then this is again the output tracking error only, just the output tracking error only, all right? Then gamma is a positive number, but the moment you translate this to discrete time, some additional conditions come in. All right, so previously we had a positive gain, so it is a positive gain. So this is a positive gain, but then you also now have to take the information vector, so to say, that you have, and then normalize it by 1 plus the norm squared. Okay, and then you will see that the all right, gamma needs to be, this gamma down here, it will come out as part of your stability analysis. It is to be positive, but it is to be positive and not larger than 2. So gamma is between 0 and 2 and positive. So this number is fixed down here already in this adaptation. Okay, gamma is just a positive number between 0 and 2. There's this normalization. So as I told you all before, I said, you look at this, particularly those of you who are familiar with stochastic updates, fast approximation to update equation, and you will remember that in all those fast updates, what they told you was that, okay, you have some kind of sensitivity function and a error, and it will look like this, right? It will look like this, your update will look like this. Then they will say that in front of it, you put a step size called mu, and you say that, look, you can update that as a fast update, and this fast update will work as long as the mu that you put here is sufficiently small. And you will see that in all of that language of this fast updates, stochastic updates, that they put a u, and u must be sufficiently small. But they don't tell you what sufficiently small is. I mean, what is sufficiently small? When I put 0.1, is it small enough? It turns out that the answer is that in some situations, 0.1 is not small enough for certain situation. Is 0.01 small enough? They also cannot tell you. Okay, whereas here, because we take a stability-based approach, I can tell you. Okay, and you'll see that coming out of the stability analysis too. The number here, gamma, needs to be between 0 and 2, positive, but between 0 and 2. And with this normalization down there, all right, I can guarantee you, as long as you put gamma between 0 and 2, and with this normalization, I guarantee you that this updating is always guaranteed to be stable and tracking error will go to 0. I guarantee you that. Okay, but in the next file, I'll show you the stability analysis. All right, so there's no such thing as sufficiently small in the way that we are doing this update. All right, because in the way that we have constructed this part of it, a gamma positive but between 0 and 2 with a normalization of the sensitivity vector, right? All of this guaranteed for me my step size is correct. Okay, no such rubbish as sufficiently small. Okay, because I is exact. Okay, so anyway, so you put that all together, and then similarly, okay, as before, it turns out like that, right? It turns out like that. With again some very careful signals and systems called the key technical lemma, right? Then what will happen is that the discrete time adaptive controller, okay, you see that coming up, right? Let me again make it smaller. So this is your system, your typical discrete time system. All right, then you will set up again, all right, a reference trajectory that you're trying to track. All right, then what will happen is basically this is what you will do. All right, your control law will be like this. All right, so this is a set of signals that you have. These are all signals that you have. I mean, y at the current time, one step later, and depending on the system, okay, basically it's n signals here, n signals here. Right, and then as long as you do it this way with gamma, a positive number between 0 and 2, I also can similarly guarantee you that everything is bounded and tracking error goes to 0. Tracking error goes to 0. But you will also note that similarity, that this is all I can say. I cannot guarantee you that the parameters that I adapt will exactly go to the theta star. All right, and again, the idea of persistency of excitation will come in. All right, so it will come up. Okay, just to quickly show you why this comes up in this way, and I can guarantee you this instead of saying you give me sufficiently small step size without being able to tell you what is sufficiently small. All right, so here I tell you exactly, and this result is guaranteed. This result is guaranteed. Okay, how does that come about? That is there in that last file. All right, you see the stability analysis. All right, so with this down there, okay, you go ahead. Basically now you're working step by step now. So instead of looking at V dot, you're looking at how V increments with time. All right, and then you go ahead, work on all these things. And then finally, what you will see is that this whole thing comes up, you rearrange it, All right, because what happens now is there's a difference in discrete time evolution, right? Because in discrete time evolution, you will suddenly see that, okay, basically this V dot, okay, this V dot of your continuous time. But because in continuous time, you know, your step sizes are infinitesimal. Your signals are smooth and infinitesimal. So basically, you know, the measure is, time measure is infinitesimal. But here, step size are definite. And because step size are definite, what will happen is that after you do this increment, which is similar to V dot and yet different because it's discrete time, you will see this now, okay, this now expands to be, all right, 2 phi. This is the parameter error, which here I call it the theta tilde. Basically, it's phi. All right, so this would now be phi squared down here. This phi squared down here. All right, but there's a second component which is increment of phi squared. Okay, you can see how you can always somehow by cleverly designing your adaptive update, because sorry, this is not phi squared. This is phi transpose phi dot. Okay, this phi transpose phi dot. So phi transpose phi dot is always there, and phi dot you can always design it such that this part has negative semi-definiteness. This phi transpose phi dot. But you see, in continuous time, this second order term never comes up, because in continuous time is infinitesimal increments in your signals and system. So this second order term never comes up because this second order term is negligible. But in discrete time, because it's step by step, this second order term is not negligible. Okay, so you've got to take into account that. So that's why we have to handle that carefully. So you see, we handle that carefully. Then with the second order step size, we have to overbound it. All right, we have to overbound it. And then when we rearrange, we say, okay, it's overbounded by above. And the moment we overbound it by above, all right, you suddenly begin to see that, okay, instead of V dot equals to E1 squared, it doesn't come out to be E1 squared alone. It comes out to be minus gamma, 2 minus gamma, 1 over norm of your sensitivity vector squared. Okay. And then that's where the condition on gamma needing to be between 0 and 2 comes in, because this V dot will now be only less than or equals to 0 once you ensure this whole part down here, all right, is so. This part, bottom bar is always positive. This is also positive. There's a negative sign. So in order to make sure that this first part is always also negative, you have to make your gamma between 0 and 2. So that's how that comes up. But that maintains that V dot less than or equals to 0 for you. There's an E squared. So similarly, what will happen is that you can basically integrate through. Here you're summing through, and you're getting square summability as well. Right? You can see now why it's like that. Okay, whereas, you know, in continuous time, as you adapt, as I said, is infinitesimal. So it moves smoothly along the curve. So the moment you get the direction right, you are moving smoothly, and the second order terms never bother you. Whereas in discrete time, okay, you're moving in the correct direction, you may be correct direction, you move correct. Correct direction, you move correct. Here you move correct and you're nearly near what you want to do. But supposing your next step size, if you don't do it properly, you know, and you have to manage your step size, here it's guaranteed. But if you don't manage it, that's why the stochastic approximation, people have to say you have to make it sufficiently small. Because, you know, your next step size, you know, is not going to be infinitesimally smooth, like continuous time and then go all the way here. Instead, if your next step size is such that it is this kind of a size, the next thing it will do, it will still move along the curve, but it will jump here. So instead of, you know, going down, you have actually jumped up. So that is why, you know, in discrete time, this kind of other things come up. Now, then there's the additional part of the so-called key technical lemma, which is also signals and systems, which is equivalent to what I've said to you before. Then finally, with that, you can combine all that together stage by stage and show that even for discrete time, indeed, if you do it in the way that we have shown, all right, which is in this way. All right, that the adaptive control is also guaranteed to have this kind of result. All signals are bounded, and then tracking error goes to 0. Okay, of course, if you now want parameter to go towards theta star, then somehow you have to look into that additional situation of so-called persistency of excitation. All right, so with that, those are the things I just wanted to point you ahead to. As I said, all right, all the things required for the examination were done up to the end of last week's class. All right, so you better be very familiar up to last week's class. All right, up to last week's class, those were 5104, 6104, all those things are for exam. For today, essentially, as I told you, all these parts are not for exam. But as I wanted to show you, all right, it's not difficult. That's why all that we have done up to last week is very important, because those are the key fundamentals. And whatever is being done here, even though, okay, there's some messy details, but you can see it builds upon those same ideas. Builds upon those same ideas. So that's why I'm not worried. Okay, so that's why I wanted to show this to you. And with that, I'm done with my part. So I'll stop the recording.